Hey everybody, Adam Savage in my cave, and I recently came across an article about a designer and prop maker named Ryan Norbauer, who is obsessed with many things, but among them are mechanical computer keyboards. His mission for the past 5 years has been to build what he considers the perfect mechanical keyboard, and this is the fruit of his labors, a beautiful and precisely crafted object called the Seneca. This weighs almost 10 pounds, and precisely crafted might be an understatement. This keyboard is hand-assembled from 700 custom parts, takes half a day to assemble each one, but the most interesting aspect to me is the intense mechanical problem solving that Ryan had to go through to fix what is considered one of the great unsolved problems in keyboards, and that is the clacky clack of the spacebar. I love this. I think that some of the most interesting and amazing things human beings achieve are when they have a really specific point of view on a problem no one else is thinking about, and they work so hard to execute that point of view. So we reached out to Ryan, and he gracefully invited us to his workshop to take a deep dive into how the Seneca is designed, how it's assembled, and just what it took to fix the spacebar problem. Ryan, first of all, I really appreciate you letting us into your process, and I really love this layout you've prepared. Walk me through this. What's going on here?
Sure. So the Seneca is probably the world's most insanely, irrationally hyper-engineered keyboard. And as a machinist and person who thinks about fits and tolerances, I thought some of these things might be interesting to you. Particularly, I think, as an example of the amount of effort and thought that I put into the creation of this keyboard, I think the stabilizer is an interesting kind of case study in that.
The stabilizer is the thing that allows the spacebar to be pushed anywhere along its length.
Yes.
And contact.
So spacebars have at their far ends these extra stems, right? Yeah. Because essentially it becomes a lever and a seesaw if you didn't have some mechanism on the long keys for stabilizing them. So what a stabilizer does is it pulls down, when you press on the far end, if you do that, it will pull down this other side at the same time, so it doesn't go like that, right? And so these have been in keyboards for a very long time, including enthusiast keyboards. And there's a standard way of solving this problem, and it's this. So there's a wire that runs from this side into here and makes a right turn, and it connects into these sliders and plastic housings. And so this actually solves the problem quite well in that when you press here, the other side doesn't seesaw, it goes down at the same time. So that works well enough, but the problem is it's kind of rattly. So the wire moves around inside of that, that slider, right, where it lives. And so what enthusiasts do is they buy a keyboard, like something like this, but without the metal housing. And then they'll take it apart, and they may have to desolder all the switches and then disassemble these stabilizers, and they inject a high viscosity lubricant into the interstices. So that, it's actually not for lubricating, but it's the viscoelastic property of the material. So what it does is it takes the sound and it turns it into heat, right? Oh. And so it absorbs it, and in the same way that like rubber would if you hit metal against rubber, right? Right. I'm assuming I have the science right. You probably would know better.
I think you've got that right.
And so that's fine, but the problem is that you can't do it extremely reliably if you are producing keyboards at scale.
Right.
And
it's laborious.
It's laborious, it seeps away over time, and so it changes.
Oh, okay.
And so as a result, it's very, it's just not good if you want to deliver keyboards to a high-end user and
with
you want to do it.
Specific needs and desires.
Yeah.
So while this had an excellent solution out of the box and an excellent modification solution, neither of those was acceptable for you.
It seemed to me like the fundamental architecture of stabilizers is a little flawed. And the community solution is not one that is like really as elegant and scalable as I would like it to be. Right. So I had this idea, I've made aftermarket housings for keyboards so I've been at this for 10 years. The first 5 years was aftermarket. So you were just providing really nice outer cases for existing keyboard layouts. Upgrades. So this keyboard, for example, is the first one that I made. I made the prototype on a World War II Bridgeport mill at the Artisans Asylum in Boston.
Oh, that's great. I know that building very well.
Yeah. I saw your tour with Derek. It was very cool. But so on that old Bridgeport mill, I made a prototype for this. And this was my first project. This keyboard here is an aftermarket housing for another keyboard made in Japan, sort of highly prized by enthusiasts. But what you'd have to do is you'd have to buy this keyboard from Japan, which is hard to obtain,
Right.
very expensive. Then you have to void the warranty, take out the guts, put it in one of my housings. My housings are also hard to obtain because they're made in very small volumes.
Yeah.
And it's a big ask for people.
So you were also, during those runs, you weren't selling a whole assembled keyboard. You were selling the housing to people who would then go and put it in that keyboard after obtaining.
Exactly. Aftermarket upgrade purely
Gotcha.
for like the first 5 years. This keyboard is called Real Force. And you buy it in a plastic injection molded housing, and you just pop it out. And there's like a metal plate that comes out of it. You put it in, screw it in, that's it. This one, however, is from a keyboard called the HHKB.
Yeah.
The original keyboard is, the switch plate is integrated into the injection molded plastic housing.
Oh no.
So you can't just pull it out. You'd have to like, grind it off with a Dremel or something. And that's just, not a very elegant solution. So what I had to do was recreate the injection molded plate, reverse engineer it,
No.
so that you would take all the guts out of the inside, put it into my metal housing, including this, but you would take the PC, basically all you would take is the PCB and the sliders from this, $300 keyboard that you just destroyed and voided the warranty on.
I'm sorry. I'm just reeling from you reverse engineering this part that no one will ever see again.
That's right. It was a multi-year process, but that's why it's called the Heavy Grail, is because I made all of these other ones, and they're like, well, the last one in the line is the HHKB. Why haven't you made a housing for that?
Right.
And I would get this question constantly at keyboard meetups, and eventually I'm like, okay, to keep myself engaged in this essentially recreational business, I'm going to try it. And so that is the result. I originally tried doing like urethane molding and 3D printing and milling, and just none of it gave the right feel and sound. Keyboard enthusiasts are extremely sensitive to acoustics and smoothness of travel of the bearings. And so this was just the only way to solve that problem.
When you started injection molding these, did you find that the formulation of plastic even mattered to the sound and performance of this part?
Yes, absolutely. The original is ABS. This, I won't say it has to be ABS, but in order for people to perceive it as having the same magic as the original, it has to be that ABS. It so happens that ABS and polycarbonate have the same shrink rate, so you can share a tool between them. And so we did PC and ABS, and some people actually prefer the polycarbonate because it gives more of a clack. ABS is more thocky, it's sort of deeper sound.
Wow.
So the answer is yes, people care deeply about this stuff in the keyboard community.
That's amazing.
But at any rate, this project was hard, right? And so it just like gradually increases my ambition for what I can do and keeps me engaged.
Yeah.
And after this, I'm like, well, I guess to not be bored, I just have to make a keyboard completely from scratch, where I control every single component.
Well, I figure once you've done that, you've tackled something that is in and of itself harder than any individual key to design in my head. That's what my head tells me.
I wish that were true. That's what I thought at the time.
Fair.
But
this gave you the courage to proceed.
It was a misdirection, but nevertheless.
It was the wrong information.
I often say, but particularly about the stabilizer project, like had I known what would be involved in getting to the place where we got, I would just have abandoned keyboards on the spot.
Wow.
Just because of the circuitous path. But it emboldened me. I think, injection molding, okay, I got this, no problem. So I had this vision for a keyboard completely built from the ground up, where every single component is custom tailored to what we as keyboard enthusiasts have come to know makes a keyboard sound and feel great, or at least my subjective expression of the perfect keyboard. And so because of my sort of naive ambition and being emboldened by the Heavy Grail project, I'm like, this can't be a hard problem to solve. Surely, like this rattled problem is just like factories making these at very large scale and probably just being lazy with the tolerances, right? Like they're being sloppy. All you have to do is like tighten up the tolerances. Surely it'd be fine, right? They just hadn't thought of it, right? And so I experimented with different, like fundamentally different approaches. So the first one was the most naive and stupid. It was, so the idea was you just take these Drylin bearings. Are you familiar with Drylin?
No.
It's a thermoplastic that has lubricant sort of baked into the material. So that as the material abrades away, it actually releases lubricant and it becomes smoother over time.
So wear and tear actually improves its performance to a certain
exactly. And so I'm like, well, a stabilizer is basically a linear bearing, right?
Right.
And so what would happen if we just took these two stems and we put very precision machined cylinders in there?
Sure.
Right? And you put them through these holes, you got a linear bearing, it moves up and down, it's smooth, no problem. Well, of course, I tried this out. I found a company that does very precision machining of small parts in like Louisiana or Alabama or something. And it took them 3 months to make the parts for me. It was $2,000. I got like a handful of them. And, I put them in my precision machine fixture with these dryland bearings. You push it down and of course it just doesn't pop back up. I'm like, that's interesting. That didn't work. And so what I didn't realize at the time and subsequently learned is whenever you have a linear bearing, what's known as the diameter, which is the spacing between the contact points and the length, relates to the quality of the slide. So if you have, like, the perfect bearing is a long sleeve over a cylinder, right? Because there's a long space between the two contact points, and the diameter is small relative to the slide. But you can think of a worst case scenario as if you had like a short sleeve, right? And another short sleeve between two widely spaced poles. It's going to bind immediately.
It's going to rack. There's almost no way to get it to mechanically not bow here because the lever arm is too long.
Yeah, it's known as the moment arm. Right. So the more distributed away from one of the contact points, the more force is put on it, and the more it's going to like take it out of line and cause binding. Well, a stabilizer, because we want keyboards to be thin, is like the worst case scenario for the bearing ratio, because it's a very short travel, very widely spaced, especially on a spacebar. But one of the ways you solve a problem of a problematic bearing is you just put loose fits, right? So it gives you play.
You remove the binding.
You remove the binding, right?
Wow.
And so, as I would later learn, there's kind of like a trio of things you can have. You can have free movement, you can have good acoustics, and/or you can have a combination of keycap width variability. So that's another problem with this, is these two space bars are made by different companies.
Yeah.
And so the spacing between these stems is going to be a little bit different always, especially for long, injection molded polymers like this. The shrinkage rate is hard to control.
Sure.
Right? And so any stabilizer that works has to be able to accommodate, like a millimeter of difference, right?
Right.
And so as a result, if you tighten up those interfaces, it binds, right? So you can have one of those or two of those three things. You can have free movement, good acoustics, or a combination of spacebar variability. Because I started making my own stabilizer housings and sliders like this.
Oh, copy.
And I bought a Foreign Labs printer, and then I got a lot of like super high resolution prints from Proto Labs. Like a handful of these is $2,000.
Oh my God.
I even tried stuff like overmolding the wire in rubber like this, because that's where the contact point is with the slider that creates rattle.
Right.
But the overmolding, like the temperature of the overmolding does something to the metal.
No.
And it throws out the tolerance just enough that it will cause binding.
I'm sorry for yelling, but that's crazy.
that's how sensitive this system is to the slightest change, right? So it's not by accident that the slop is here, right? It's because it wouldn't work otherwise. So eventually I realized this, and I realized that this is a problem beyond me as a tinkering industrial designer who barely knows mechanical engineering. So I just saw somewhere on YouTube, I think it was Veritasium, is that?
Sure.
He had a video about compliant mechanisms.
Yes, I love that one.
And this is an example of a compliant mechanism. It's a hinge, a living hinge that has no separate parts.
Right. It's one piece.
Right. And so you can create all of these surprisingly complex movements with injection molded or plastic or even metal flexures.
Yeah.
And I'm like, well, conceptually, that's the solution to our problem. We need to get rid of rigid bodies banging against each other.
Yes.
Right? So maybe I could find somebody who knows how to do this in compliant mechanisms. And so I did a lot of Googling, and I found a company in Denmark called RD8, which does I would say sort of luxury consumer product engineering consulting. They've done stuff for Aldi. They when the people at Lego have a hard engineering problem, they go to these guys.
Oh yeah,
right?
Okay, there you go.
They know what they're doing.
Yeah.
They're very expensive, but they had an article about compliant mechanism design. I'm like, okay, maybe these are the guys I should talk to. And they instantly knew this is a bearing ratio problem. And so they said, well, actually, we could probably solve this for you without a full compliant design. Because there's actually one problem with compliant mechanisms, which is that if we use this on a stabilizer, it would have a variable force curve. Like once it, the material compresses a lot, it has more resistance.
Right.
And you don't want that. It would have like a squishy feeling. You want the stabilizer to kind of disappear.
Yes.
Because it should feel like a normal switch, just stabilized.
Yeah.
Right. What we could do is do this like hybrid solution, which is this one. And so I would take the keycap off, but then it would probably break it because these are just 3D printed
Copy.
Parts. But what they do is inside of the slider, there's this little spring, which is actually a compliant mechanism.
So it's a little V at a spring steel.
Yeah, and it pops into the slider, and it basically just presses down on the wire very, very lightly.
The same wire that is in the regular key that helps the other one come down.
Yep. So this is actually a very minimal change from the existing designs that are used widely throughout the keyboard community.
You had intuited that there was a change that was potentially available, and here it is.
Yeah, so this is a kind of hybrid solution. It's not fully compliant. There are separate rigid bodies.
Right.
But as a result, you can probably tell just by playing with it.
Yeah.
There's a lot of rattle there.
A ton more. And this one's very, very...
You hear the plastic parts moving, but not metal rattle.
Well, and also you can feel on your finger the more stable movement to it.
Yeah, absolutely. It actually performs the stabilizing function better because it is actually, in many ways, a tighter tolerance part.
Right.
The really critical insight they had, and it's something I'd never even thought about before, but on reflection, it's obvious. If you had a 300 millimeter part and you want to machine that to plus or minus 0.1, that's harder to do than a smaller part, right? It's easier to hold tolerances over shorter distances.
Yes.
Right. And so the standard stabilizers actually, they have these rails that are spaced pretty widely that control the movement. So like the sort of X and Y translation, right? Here, what they've done is they've moved it to this very tiny little interface, which we call a tongue and groove interface. And so it's a relatively very small dimension.
Right.
And as a result, we're able to control tolerances much better and tighten up that gap while still having a clearance fit. And the interesting thing about the geometry of it is the slider can move this way laterally.
Oh.
And that actually is what accommodates for space cap width variation. So we actually have this really tight movement here, but we can go this way.
But it's constrained only in the direction it needs to be constrained,
Yes.
and it moves where you want it to move.
Yep.
Wow.
So that's part of how we got to this really good place of a much better, much improved stabilizer.
Yeah.
But they had another insight about this, what was not working with this, which is that this design is over-constrained. There are redundant interfaces in it.
Oh.
Right? And this is kind of their specialty. They told me that when clients come to them with mechanical design problems designed by professional mechanical engineers, 90% of the time, the designs are over-constrained. So they sent me this amazing sort of demonstrator model here. So 2 sliding linear bearings, right? They both work just fine, but they're not robust to variation. So if you have, or one of them isn't. So if you have the rods slightly out of alignment, that's what this does.
Oh, okay.
One of them works just fine, but one of them binds. This one is robust to variation, and this one is not.
And that just means
So why
that
is
there's,
that?
I would assume that means there's a greater tolerance between the rod size and the hole size on this one than there is on this one.
So that's one way of solving over constraint, is just tightening tolerances.
Right.
But that's a bad way of solving it, actually,
Sure, yeah.
because it's expensive and it's hard to control. Actually, what you need to do is control the interfaces so that you're not over-constraining the design. A better way of demonstrating what is different about this is this.
That the contact point is more...
Exactly. So one of these holes is just intentionally too big. So it's not touching in any way.
Right.
There are only 3 contact points here, right? So it's essentially this, right? Internally.
Right.
So that still moves and that binds up. And that's the problem with these stabilizers, is they have redundant contact faces and rails. So they're over-constrained, making them extra sensitive to the buildup of forces. Because of the special problem of stabilizers and the extremely bad bearing ratio, it's sensitive to the slightest thing. So whenever you try to turn any dial on this, because of the overconstraint plus bad bearing ratio, everything goes out of whack.
Right.
So their idea is, well, let's just solve that by removing the overconstraint, and it buys us a little wiggle room to add features and add forces that will not cause binding. And that's why we're able to add the spring to this design. We're probably 3 years in.
Yeah.
This was the first year was just, or first couple of years was just me. This is working with them for a few months. And I'm like, there's still a little gap between that tongue and groove interface. There's like two, in the keyboard community, we have two words for this. There's rattle, which is the sound of the wire banging around it. That's the more severe problem. But there's also a subtler thing known as ticking, where the slider moves against the housing. And if you just tap it a little bit, you can hear it. Oh. People don't like that. I don't like that.
Fair.
And so if you're going to make a perfect keyboard, you kind of want to make it impossible for that to exist. And one way to do that is I could just put some lube in there.
Yeah.
But what was the whole point of this project, right?
Right. It's to not have lube and not have a change in performance over time as well.
Exactly. And just have it just be like a conceptually pure solution to the problem. So one thing that they had mentioned to me in the process of developing this was, well, there's like a theoretically perfect solution to this problem. We could use pin joints, because then there's no flat surface in any way that touches any other flat surface. And in fact, that is one of the characteristics of the Seneca. There is no hard surface anywhere in the keyboard that touches another hard surface without a gasket or some mitigation mechanism.
Oh, wow.
No sort of moving functional parts. Because that's where bad sounds come from, is flat, hard parts hitting against each other and resonating in unwanted ways. One way to get rid of flat, hard parts hitting against each other is to use pin joints, because they roll against each other. And they're kind of one of the design heuristics that RD8 uses is like, whenever you can use a pin joint, just use a pin joint because it's better. Here, we can see there are many pin joints on this scale model of our stabilizer. These metal things are pins.
Right.
And one interesting feature of a metal pin is that it's an order of magnitude increase in precision to how what tolerances you can achieve with it.
Of course.
And so when we're trying to get rid of gaps between parts, that's extremely important. So effectively, you can get zero clearance parts if you have extremely precision ground pins, and then you have reasonably precision injection molded interfaces. When they showed me the model of this, I was like, that looks really hard. Like, because it was just a conceptual model, it wasn't fully fleshed out. I'm like, I don't know, it makes me nervous. I'm 5 years late on shipping this keyboard.
Right.
Do you think we could maybe do the faster thing? But then it just nagged at me. Once we finished this and we were ready to move into production, I'm like, I don't know, maybe we should do the perfect solution.
Right.
And just see what that looks like. And so we did. We sort of plunged forward into another set of extremely expensive sprints, and this is what resulted. It's a pin joint, fully pin joint mechanism that has no flat faces striking against each other. We even have some of the concepts from this one built into it. So right here, there's a little preload beam.
Right.
It presses down on the wire just a little bit.
Just to hold.
And it prevents it from rattling.
Right.
Because that's one place where we're not reaming holes. Right?
And just to be clear for the audience, like this distance here can change and be very wide in this mechanism because of the pin joints still stabilizes perfect.
Yep, we just changed the length of the wire.
Right.
There are actually, on every keyboard, there's 5 stabilized keys. Backspace, enter the 2 shifts in the spacebar, and they're different lengths. And so we just make a longer wire. Otherwise, the geometry is the same and the kinematics are the same.
Oh, fascinating.
And so this is what resulted, and it does what it's supposed to do. There's effectively zero clearance. We just added another preload beam here at the back to prevent the wire from rattling there. And one downside is that in order to build a keyboard with these in it, it takes like half a day. It's like a sort of precise
of adding these 5 keys.
Yeah, I mean, you'll see what it looks like to build a stabilizer when Teja shows you. But that's kind of the premise of this keyboard, is like, just go crazy.
Yeah.
What would it look like to make a keyboard as perfect as you possibly can?
But what if you could?
Yeah.
Wow.
And so that was a multi-year, very expensive project.
Just for the stabilizer.
Yeah, but in the end, we found a way of solving a problem in a way that nobody had before.
Right, so this is unique in keyboards. No one else has a keyboard.
Correct.
No one else has built a keyboard.
We have a patent on this one and a patent on that one.
Oh, fabulous. That's
worse.
Amazing.
Yeah. And so that's just one story of like 10 different things like that. This is the most extreme, but even the switch design, I went through 3 radically different iterations, including getting tooling made for each of them, just to get the acoustics right.
Hi, I'm Teha, and today I'm going to be showing you how a Norbauer stabilizer is assembled. One thing I'm learning as I'm working here is that designing a product is one thing, but also designing sort of the assembly jigs to make your products into a reality is also another big part. So this might be new for keyboard enthusiasts, but our stabilizers require a 4-stage sort of assembly jig line process. And from the first assembly jig, we get just these 2 leaves that are connected. And then you can kind of see each part slowly gets added on piece by piece until we have the fully assembled stabilizer here. Obviously, from using these jigs, it adds some assembly time, but the biggest portion that adds assembly time is the fact that at each process of the assembly jig, we have to manually ream certain parts of the components. And the reamers that we use, first, they're very small, but also just the tiniest difference in width can be the difference between your stabilizer being too sluggish or too rattly. So for example, some components you can be a little bit more rough with, but there's one component where, for example, we are currently using a 0.82 millimeter reamer, sized reamer, and moving down to a 0.813 reamer. That's the difference between being sluggish and freely moving. So you have to be really precise. And there are some guiding mechanisms that make it a lot easier, but a lot of it is just sort of done by feel. So I will demonstrate this is the 3rd process of our assembly. So these were made in the previous steps. You sort of load it up here and they line up nicely. And they're all sort of assembled in a way such that it aids the process of working with these small components. That just slots in nicely. So I know Ryan might have mentioned that he was looking for a no lube solution. But currently we do use lube more for the purposes of just making the mechanical movements smoother. It does operate without lube. You can definitely assemble it without it, but just like how mechanical watches, the internals are all very well lubricated. If you can see some benefits in smoothness, I think we should lube. So we do currently lube, but they're not used for their traditional purposes of the bulk effect. They're actually used for the intended purposes of lubricating certain mechanical motions. So normally I'd be doing this with gloves and be a lot more careful, but because this is just for demonstration purposes, I'll be a little bit quicker. So that's one step. And then from here, I would generally check that the interfaces are freely moving. And this is where the reaming comes in. So this is sort of the part that takes a long time, and I can kind of feel when certain parts are catching, and then I have to be very steady with my hands because even just that 1/10 of a millimeter can be the difference between your previous 10 minutes of work being obsolete and being able to move on to the next stage. So yeah, this is just a little peek into how a Norbauer stabilizer is assembled.
I want to talk about, as I came into your house, I saw some mid-century furniture. And I'd like to talk about your aesthetic journey here, because while you've been describing an engineering journey, really what you're describing in my mind is an aesthetic journey. You're looking for a particular experience of the keyboard at the cost of everything else.
Yes.
And I'm so here for that. I'm just so, talk to me about your aesthetic maturation and why this is existing now.
Yeah, so I mean, I think I said in the Verge interview, like, this is not really a keyboard a sane person needs to buy.
Right.
This doesn't solve any essential problem that you can't solve with $10 or like the free keyboard that comes with your Dell.
Right.
So I think the meaning behind your question is, why do something so crazy, right? Why did I invest hundreds of thousands of dollars of my own personal money with really no confidence at all that I could possibly ever make that back into something so wacky as this? And I think about that a lot. It took me a while to kind of actually get insight into why I cared so much about keyboards in the first place. And it does actually kind of relate to mid-century modernism as your question. Because like, as I said, retrofuturism is the vibe here. And one of my favorite authors, her name is Virginia Postrel. She wrote a book called The Power of Glamour. She has this idea in it of people are drawn to escapist things in commerce and storytelling, in arts in general, because they're a little bit dissatisfied with the world as it actually is, right? And we want to inhabit or physically touch something that feels free from the disappointments of everyday life, right? And
What a beautiful phrase. Yeah.
well, I think that this is why I loved Star Trek growing up as a kid. Is, I grew up in West Virginia. I was a very nerdy, bookish, weird, gay kid. And so you feel a little bit alienated by real life.
Yeah.
And on television, there was this incredible vision of the way things would inevitably be in the future. Everybody was going to be nice to each other.
Yeah.
Tolerances would be accepted and celebrated, and everything was going to be great. So I desperately wanted to step into that world. And the story that was like deep in the culture, it wasn't just Star Trek, but you see a lot of Epcot stuff around my house. Like that was the idea at the time. Is like the future is going to be amazing.
Right.
It's right around the corner.
And Epcot stands for Experimental Prototype Community of the Tomorrow.
Tomorrow,
yes.
Absolutely. And somehow that just like, that was my escape. I was like, okay, maybe reality sucks, but the future is going to be amazing, and this is what it's going to look like. And it's intimately related to space exploration and computing, right? And so the design language of Star Trek to me is that the expression of that idea. And I heavily associate it with computing from that era. And that's why these keyboards feel like keyboards from the 1980s, right? Is for me, they embody that hope of, okay, once we're all connected to each other by the internet, surely we'll all, like, cultural differences will disappear and we'll all get along, right? Everybody's going to be so smart because they have access to infinite information. It's not so possible to believe in that idea anymore. And that makes me want to sort of escape into these perfect realms of this fantasy even more. And that's why this stabilizer won't do, right?
Yeah.
There's an emotional thing here.
And you have the power. You can. I like to talk about some of the things I achieved while making the show was stuff that I could do because I had, quote, TV money.
Sure.
I was making enough where I could allocate a certain amount of absurd dollars to things that were just interesting to me. And I felt very grateful for having that opportunity. I tell you, can I give you one perspective? What you're doing here might not make sense from commerce, but every fine artist knows this model entirely of being unforgiving about the process and then selling at a very high expense the product of that process. And I think that what you're manufacturing here are individual pieces of art.
It turns out that it's more viable than you would think if you find people who want to be passionate about the same thing that you're passionate about. And these keyboards the Seneca now has a 6 to 9 month wait list, right?
Wow.
We've sold a lot of them, and people are very excited to get them. We have clients who, it starts at $3,600. Like I say, nobody needs this keyboard. I freely admit that. Mm-hmm. We have clients who bought 2 of the $8,000 one, the titanium solid one. Clearly this resonates with a small group of people, and I just want to hang out with and make stuff for those people.
Well, and I'd like to talk a little bit also about that community, because as the whole time you were going through all of this exploration, am I right that you were communicating with that community online, talking to other keyboard enthusiasts? So this was a project other people followed.
Absolutely. Everything here is the result of things that I mostly learned from my fellow enthusiasts on websites like Geek Hack and Keep Talk and all these places where people just talk about keyboards all day long. It's an amazing community of people, actually. I've often, unfortunately, I often unfavorably compare the prop replica community to the keyboard community. Especially when I was younger, prop collecting was mostly about having a thing that nobody else had.
Yeah, there was a lot of people that got off on that specific part of it.
And that's what actually turned me off in early days.
Fair.
But the keyboard community is incredibly supportive and encouraging. Mm-hmm. And even people who operate companies in this space help each other out all the time.
Wow.
I could give you countless examples of friend companies that really do things that are not in their commercial interest just to help each other out and sort of develop this community.
Because they
together.
believe in the mission.
They believe in the mission. They personally like this stuff. They're like, oh, wouldn't it be cool if that existed? I want you to do that because I'm doing something else right now. Here's the CAD files or whatever. And yeah, the keyboard community is actually quite amazing.
I am so glad that it turned out to be viable, that it didn't actually matter if it did or didn't is delightful. I'm so inspired by this. This is just a really incredible journey. I thank you for sharing this with me.
Thank you so much.
Holy cow. That is a really nice sonic space.